In a city that never stops building, some projects move not just upward, but deep beneath the surface. Beneath the towers and traffic of Tokyo, a station was born, not in open air, but in the compressed space between earth and steel. This is the story of how gravity, pressure, and precision met in a place called Toranomon. Last week, we explored the facade design, BIM optimization, structural system, and seismic design of the station tower. This week, we will take a closer look at the underground construction process of both the station tower and Toranomon Hill Station. In 2014, a long-term vision for the Toranomon area was formulated through the Tokyo Urban Redevelopment Council. This vision aimed to strengthen transportation nodes by the 2020 Tokyo Olympics and Paralympics and beyond, ultimately creating an accessible urban transit system for everyone, including international visitors. This led to the development of a new station in the Toranomon area. The Toranomon Hills development project, led by Mori Building, began in 2009 as a TOD, Transit-Oriented Development, within the Toranomon 1 Chomen District. It began with the construction of the Toranomon Mori Tower in 2011, followed by the opening of the Business Tower and Toranomon Hill Station in 2020. The residential tower was completed in 2022, and the station tower and Toranomon Hill Station were finalized in 2023, concluding the large-scale redevelopment of the Toranomon Hills area. This project is often cited as a leading example of urban redevelopment in Japan. Just 1 year after the opening of Toranomon Hills, the foot traffic increased by over 7% and land prices surged by 34.4%. When planning Toranomon Hill Station, the site had to be positioned at a reasonable distance from nearby stations. First, the location needed to have a longitudinal gradient of less than 1% to ensure a smooth and safe ride. Next, the track required a curvature radius of over 400 meters for structural stability and operational efficiency. Only one area met both conditions, a point between Kasumi Gaisuki Station and Kamiyacho Station intersecting with Ring Route No. 2. That's where the station was built. One major constraint during construction was the shallow soil cover of only about 3 meters above the existing Hibiya Line tunnel. Because of this, it was impossible to build new station structures above the tunnel. Instead, the tunnel sides were expanded to install new platforms and the main station functions, such as the concourse, ticket gates, offices, and mechanical rooms, were placed beneath the tunnel on the second basement level. The design and construction were commissioned by UR and carried out by Tokyo Metro. In 2021, the B1 level Hibiya Line platform opened, followed by the B2 level concourse completed through underpinning in 2022. The full station and station tower were completed in 2023. One of the greatest technical challenges was the simultaneous construction of the high-rise station tower and the rebuilding of the Hibiya Line. This required deep excavation around the existing tunnel and the installation of new structures. Various advanced methods were used, including the earth drill method, piled raft foundation, superknuckle piles, top-down construction, and underpinning. The process began with a detailed ground survey beneath the future Toranomon Hill Station. Standard penetration testing and shear wave velocity testing revealed clay and sand layers down to 10 meters and soiled bedrock and dense gravel layers below. Due to this soil profile, the earth drill method was chosen. This technique uses a large diameter auger to drill and install cast-in-place concrete piles. It is well suited for cohesive soils and urban construction thanks to its low noise and vibration. The most critical part of the earth drill method is maintaining the stability of the borehole before concrete placement. To do this, stabilizing fluid was injected into the soil to form a mud cake, protecting the borehole through hydrostatic pressure. This allowed efficient work within the urban clay and sand layers. Next, static load tests were performed on the piles drill using the earth drill method. Given the enormous actual loads up to 90 meganewton on the superstructure columns, pile depths of 42 to 44 meters underground were required, with long-term acceptable support of 3,000 kilonewton per square meters. The long-term acceptable support is the maximum load that the foundation can safely support in the long term, which is the typical support for low and mid-rise buildings, but is insufficient for high-rise buildings. For this reason, the Chon-O-Man Hills Foundation was applied with a pile lift foundation that uses both a pile and a front foundation. In the pile support front foundation, the lift serves to distribute the load of the upper structure and secure sufficient support, and the pile serves as a complement to support the upper structure by suppressing excessive subsidence of the lift. In some cases, the load could not be supported by conventional piles alone. For example, two Y-shaped columns required support from 4 piles each. This led to the use of super knuckle wall piles, a proprietary technique from Obayashi Corporation. These piles form a continuous wall-like foundation that improves soil stability and reduces deformation. It was especially effective given the proximity to subway lines and roadways. Next came the earth retaining construction. Retaining walls are essential in urban excavation to prevent soil collapse and protect nearby structures. Common techniques include H-pile with lagging sheet piles and cast-in-place piles. In this case, the SCW soil cement wall method was used. It involves mixing the excavated soil with cement slurry using a multi-axis auger to create a continuous soil cement column. While Korea often uses 3-axis machines, the weaker Japanese soils led to the use of 4-axis equipment to enhance stability. SCW was ideal here due to its excellent water tightness and minimal vibration and noise, making it highly suited for city environments. It effectively addressed the site's loose sand, clay, and groundwater conditions. To shorten the construction schedule, the top-down method was used. External basement walls and columns were installed first, and then excavation progressed downward while structural elements were built from the ground floor down. Column sizes and rebar arrangements were standardized. Rails and struts supported H-pile walls, and the SPS method was used to combine H-piles with lagging plates. This reduced stress imbalances during demolition and allowed simultaneous above-ground and underground work. Under the B1 Hibiya line, further excavation was needed to create a new B2 level. However, simply digging beneath the existing tunnel would have compromised its support. Underpinning was used instead. First, soil was excavated to a depth of 15 meters on both sides of the tunnel. Then small tunnels were drilled underneath the line, and jagged piles and steel frames were installed to support the structure. This allowed for safe excavation below. Finally, soil stabilized with injected slurry was carefully removed. and concrete was poured into the created voids to form the new structures. Additional retaining walls were built around the site to prevent water ingress and ground settlement. Through these combined techniques, the construction of the station tower and Tournament Hill Station was completed with both stability and efficiency. Underground, where concrete meets silence and light has never touched, a new kind of space was made, one that holds the weight of a tower and the movement of a city. With each method chosen, not for convenience, but for necessity, the construction became more than a process. It became a quiet negotiation between earth, time, and people, completed not just with machines, but with understanding.